This year's science team embodies the spirit of collaboration and cooperation, proving that the whole is more than the sum of its parts. Let's see what they do.
We started as the Center for Radio Astronomy Techniques and Technologies. Now, radio astronomy is a very techniques-intensive branch of science. A radio telescope, such as MeerKAT, does not actually give you a direct image of the sky. Instead, you get a stream of numbers, terabytes and terabytes of data every hour, and then you need to do some fancy mathematics and software in order to convert that into an image of the sky. The problem is, these signals are corrupted on their way down to us by the atmosphere, by the electronics in the telescope, etc., etc. So we have to do a lot of work to undo these corruptions before we can actually make those beautiful images. And the devil of it is, the better your telescope, and MeerKAT is this beautiful, exquisitely engineered machine, the more subtle problems you have to worry about. So that was our original mission at RATT, basically develop software and techniques to make these images better. But if you're doing that, then of course you're going to need scientists to test drive those techniques for you.
Rhodes researchers and alumni were central to South Africa's entry into the international SK project because of unique experience and knowledge gained in the development of HeartRAO National Facility. They have also played a major role in the realization of the MeerKAT radio telescope. Since its establishment, RATT has become a preeminent hub for training and research and innovation in radio astronomy, with its research products and alumni making a significant impact internationally. This award is the culmination of more than 5 decades of transformational radio astronomy research and development at Rhodes University.
I'm one of the RATT researchers focused on science coming out of MeerKAT and an alumnus of SAREO's Human Capital Development Program, which is an initiative started by SAREO's Kim de Boer, which makes groups like RATT possible in South Africa. My team's research area is extragalactic science, specifically galaxy clusters. These are the biggest things that we know of in the universe that are held together by gravity. They are very dynamic environments with many complex parts. We're trying to understand why some clusters shine in the radio band and others don't. So understanding the physics behind this and how the radio signals evolve with cluster properties and cosmic time. So in preparation for the SKA era, we're also investigating image analysis techniques with machine learning using MeerKAT data as a testbed.
The RATT Center has a growing and dynamic team of young radio astronomers who use the 21 centimeter line emission, also known as H1, to address some of the critical questions on galaxy evolution. H1 is the simplest, most abundant atom in space and a key ingredient in the star formation process. The high sensitivity and exquisite angular resolution of radio telescopes such as the MeerKAT allows us to detect the 21 centimeter line in large-scale galaxy volumes. With these large data sets, we can study where galaxies form stars, how they evolve, and eventually become inactive, essentially studying to what extent nature and nurture play a role in regulating galaxy evolution. The knowledge exchange between the science and technical team at RATT and its international collaborators has been vital in developing cutting-edge H1 analysis software and techniques. This gives us the ability to make detailed H1 galaxy images.
Electromagnetic compatibility, EMC, is critical to minimizing interference, maximizing spectrum efficiency, and enabling the full benefits of wireless technology in radio astronomy and other fields. RATT are some of the most advanced radio frequency equipment for EMC metrology, which can be used to develop techniques to identify and mitigate interference. We are also involved in collaborative instrumentation projects, such as the Transient Array Radio Telescope, TAT. RATT is collaborating with SAREO to deploy TAT across the 8 SKA partner countries in Africa.
When did the first stars and galaxies form? And how different were they from today? At the RATT Center, we're trying to answer these challenging questions. And we use radio telescopes to look back in time, when the first stars and galaxies were formed, when the universe was likely only 100 million years old. We do this by searching for the faint 21 centimeter line emitted by the first hydrogen clouds. These observations require the construction of dedicated radiointerferometric arrays, like the precision array to probe the epoch of reionization and the hydrogen epoch of reionization array, both built in South Africa. The detection of the faint 21 centimeter signal requires a careful separation from the bright foreground emission and an exquisite calibration of the telescope response. In other words, an ideal ground where the RATT original mission meets science, and science needs RATT to happen in a walk together towards a Nobel Prize.